All right. As Jason said, my name is Stephen Royer. I've just a little bit about me. I've been at Red Hat for about 3.5 years now. Before that, I spent a couple of decades at IBM. Only the last few years of that was AI related. Before that, it was a lot of firmware and hypervisor work. But in terms of AI work, it's been really exciting coming back to Red Hat and working in the AI space. So let's get started. All right. So first I'm going to start off with, what is Triton? And just to be clear, this is Triton, Triton Lang, sometimes called OpenAI Triton because it is managed by OpenAI. This is not NVIDIA's Triton inference server. If you were here for that, I'm very sorry. That is not what we're going to talk about today. And I do get that question about once a month as someone confused about that. All right, so Triton came as a research project out of Harvard. It was published in about 2019. And then it was originally C-based. And so they provided a C-based language, C-style language or DSL to write your kernels for running on a GPU. And this had a couple of novel features. So one of those is that it used something called intermediate representations from LLVM. So it was a way for you to lower your language. It's a compiler technology for lowering your language down successive levels as you get towards the actual hardware. And what's great about the IRs is that you can apply different kinds of optimizations at different levels, right? And it's a good way to keep your compiler organized. The other really interesting thing about Triton is that rather than being thread-based, it's tile-based or block-based. So you write your kernels around blocks, so 1D or 2D or maybe even 3D blocks of data. And it makes it a little bit easier to manage. And then Triton deals with scheduling those blocks onto the actual hardware. And then sort of lastly is, they built this whole infrastructure around MLAR and the compiler and made it so that they could use a JIT, a just-in-time compiler, to compile this stuff onto the specific hardware that you're running on. They can run it with an auto-tuner and come up with sort of the best parameters to use for your specific hardware. And it can do it all at runtime. So what is Triton today? So you may notice if you've looked at Triton now, it's definitely not C-based. It's a Python-based DSL. So that happened when Triton was picked up along with its creator by OpenAI. But Triton really sort of took off in 2023, which you can see on here as the number of contributions, the number of contributors, which corresponds to when PyTorch picked it up as part of its Torch inductor stack. So that's when it really started taking off. We just recently had Triton release earlier this month, Triton 3.3.0. And so that's exciting with some new support. When Triton started, it was all just NVIDIA, right? It only ran on NVIDIA hardware. As time has gone on, now there's many more options. There's a lot of forks of Triton. There's also support for AMD directly in the main upstream Triton. And many vendors have Triton support now. All right, so why should you use Triton? So first, let's just talk about custom kernels. There's times when custom kernels are useful. In some cases, you want to optimize for your very specific use case. So one recent example is DeepSeek. All right, so DeepSeek put out, when DeepSeek came out, it had Triton kernels in it for doing quantization, dequantization, and lower precision mapmul, right? that was a very specific use case that was highly optimized for their model. Another main use for Triton is fusion. So when you have a sequence of operations and you go to run one on the GPU, right? It's going to load the input data from GPU memory. It's going to operate on it. It's going to store it back to GPU memory. And then you go and load the next thing. It's going to load stuff from GPU memory. It's going to operate on it. It's going to store it out. Well, if you don't need that intermediate state, you can fuse those things together and avoid the extra cost of the extra tax to the memory bandwidth for the extra save and load. And then sort of lastly is we've found through some experimentation that you can actually use it to just reduce overload or overhead. So even if your Triton kernel is slightly less efficient than a vendor provided highly optimized kernel, if you don't have to go through so many layers of software to access it, it still can be more efficient. And so even if you take the Triton tutorials and they've got a matmul example and run that on hardware, and it compares it to running the same operation in PyTorch, which under the covers, like if let's say you're running on NVIDIA, it's going to go and it's going to call QBLAS, and it's going to use the gem kernel from QBLAS, which is highly optimized. But the Triton one still does better, just because there's fewer layers in between. All right, so why Triton specifically? Largely because it's so much easier to write Triton kernels than it is to write the vendor-specific APIs. You can get a good performing kernel with much less effort using Triton than you can with the vendor APIs. And then, of course, now you're also not vendor locked. So I'm just going to briefly cover a very basic example. So this is what a Triton kernel looks like. So this one is just a vector addition with a scalar. So alpha is a scalar, x and y are vectors. And so you can see at the top, you've got like an auto-tuner declaration. You don't see all of the different block sizes that I'm showing, but that's there. We're telling it we're going to use JIT. And then you do a very small amount of setup so that you know in this particular instance of this kernel, which block is my block? What am I working on? Then you're going to load the data, do the calculations, and store the results out. It's really pretty simple. All right. So that's what Triton is. So let's talk a little bit about Triton at Red Hat. So we do have it in some products today. So Red Hat Enterprise Linux AI or RHEL AI and OpenShift AI both have it. And so the question is, well, why do they have it? Because they use PyTorch and because they use VLLM, right? And PyTorch and VLLM use Triton. And so those are there. VLLM has very specific Triton kernels that it uses for a variety of reasons. And PyTorch can actually generate Triton kernels through Torch Inductor. All right, I'm going to ask Luca to come up here and talk about neural magic.
Thanks, Steven. You guys can hear me, right? So I was recruited to present this slide like 30 minutes ago. So if I wing it a little too much, please excuse me. But yeah, I've been at Neural Magic since 23. We got acquired by Red Hat somewhat recently, but what we do hasn't changed at all. We are working on VLLM. VLLM is an inference server for very fast LLM inference. The goal is to be kind of the de facto LLM inference server. It's an open source project, just like everything else Red Hat does. And yeah, we use a lot of Triton. So I think Steven already touched on kind of a lot of the, sorry, Steve, my bad.
I'm good either way.
Steve touched on a lot of points of why Triton is so helpful, and kind of specifically in the VLM context, right? Like developing a new kernel is a lot of effort. It takes a lot of time. VLM is very much in a state of we're moving very fast. New models are dropping all the time. New optimizations are dropping all the time. and we want to kind of keep current with that. And so Triton can be a very fast way to get something working really fast that provides almost all of the performance, but that's not it, right? Like that's not all of the benefit. A huge other benefit is also the portability, right? So there's certain, there's, for every vendor has their own way of writing like the most performant kernels possible, but that can be like something we might not even be familiar with or have expertise in if the vendor is a little bit more niche. But with Triton, we can kind of abstract all that away. For example, on NVIDIA, we use a lot of Cutlass for the very, very performant kernels. There's not always an equivalent on other platforms. So even if on NVIDIA we might want to push further for the performance, that might not be the case for other platforms. So we might stick with Triton even for like the core operations that take up a lot of the large percentage of the runtime. And then there's also a lot of operations that just don't take a large percentage, and so kind of the feature work and like the support of the feature is more important than like having the 100% performance. So we'll just write the Triton kernel, use it, and move on and start working on the new features, because like I said, new models are always dropping, new approaches are always dropping, and we want to stick with those. So yeah, that's what we do with Triton at VLM.
All right. Awesome, thank you. All right, so just a little bit about what we're doing. So Luca's part of Neural Magic, which is part of the product side. I'm come from the office of the CTO. So we work on looking at new technologies that are on the horizon, seeing what's interesting, and do proofs of concept. And then if we find something that's really good, it works out well, we can then work with the product team, right, to bring it to product. So here's a few of the things that we're working on right now. So we've got Triton developer containers. So the idea there is around making it easier for developers to write Triton kernels. Also make it easier to make changes to Triton itself. Next is pre-caching of Triton kernels. So we talked about how it uses JIT and an auto tuner for running the actual kernels, right? So it compiles the kernel and then goes and runs them. But that takes time, right? And when you want to launch quickly, you have to still wait for the compile to happen, the auto tune to happen, and that can be a significant amount of time. And then next is a new project that we're doing that's really just see what we can come up with in terms of BLAS routines. So these are very classical mathematical routines, and we decided let's see what we can do with Triton kernels. And then lastly, we had some Red Hat research looking into some additional auto tuner optimizations. All right, so just a minute on the Triton development containers. One of the big problems that we have, especially in Python space and AI in general, is that the dependency management is terrible. So one of the things that we tried to do was just make it easy. If you want to use PyTorch 2.6, we can have a container that's ready to go that has 2.6, has all of its dependencies, has the correct version of Triton to go with it, and has all of the other dependencies for the vendor that you want to do the development on, right? We provide Jupyter notebooks with plugins specific for doing the profiling work on that vendor's hardware. And that's just an example we have up there. Okay, so next, Triton cache. So pre-caching, as I mentioned, is a big deal just because it can save significant amount of time on startup. So like if you're looking at an LLM, you might be looking at time to first token. This can, if you can pre-cache and deal with the auto tuning ahead of time, then you can avoid some of that startup time. And so we're looking to package up these pre-compiled kernels into OCI container images, and then provide some tooling around Kubernetes for automatically deploying these with your application. And then lastly, some observability for the Triton cache, because right now there's really no way to know if you're hitting the cache or not. So just doing a little bit of visibility there. Okay, so next I have a little demo here, a little demo video. We'll see how it comes across. All right, so this is just showing this pre-caching and packaging it up into an OCI container and then deploying in order to save time. So this is the model we've got up here right now. So this particular example is running using AMD Instinct GPUs on Kubernetes. And this first case is what it looks like, without pre-caching, right? So you've got your application. In this particular case, it's a VLLM serving instance that's running on top of the GPU. And then this is what it looks like, when we add our extra tooling around it. We've got an init container that runs, that takes a OCI container image that has the kernels precompiled, loads them into the shared volume, and makes it available to the container image, to the actual application. And so what happens is when the application starts up, it sees the cache is there, and then can check and see, okay, if I'm going to run my application, is there a cache version of this already? And the answer is yes. Okay. All right, so next it's going to show a little bit about how it does this. There's some Kubernetes magic in here. This is using the AMD GPU device plugin. And then it's going to run the setup, this VLLM instance. So now this is where you can see that we've said, okay, we're going to use this model. We're going to be running it on an AMD GPU. It's just typical Kubernetes. And then we'll jump ahead. Okay, now we're actually loading VLLM. And then at the end of this, it's going to show some stats. And the stats are going to be like how much time it spent during the startup on each individual piece. Okay, so this is it's highlighting that yes, it's using the ROCm flash attention, and here we go. So at the end, it took about 50 seconds total to launch, and then you can see the breakdown is the ones that you want to focus on here are the model load time, the memory profile time, and then the total startup time. Okay, so it's about 50 seconds to start up. So next we're going to run it the same thing, but with that additional Triton cache getting mapped in. And once again, I'm going to skip ahead. And then you see the new times, right? And so in this case now, the total startup time was about 25 seconds, so it cut it about in half. But where you see the real benefit is on that model load time. It cut the model load time about in half. And then the memory profile time, it cut significantly from around 20 seconds down to about 5. Which you can see here, that's the comparison. So that's really the benefit of using the caching for the Triton kernels. All right, and then lastly, the Triton BLAS. Like I said before, this is a very early project to implement some BLAS kernels, and this is just a really simple case. It's that AXPY case showing it the Triton kernel compared to implementing it in Torch natively.
But you're not showing it versus BLAS itself.
That is correct, and there's a reason for that.
Just checking.
Yeah.
Okay.
Okay, so that's what I had. So if there are questions. Yeah. Go ahead, Eric.
Yeah, one question to
Luca.
Luca.
Mhm.
Yeah, you mentioned that you
Yeah.
use Cutlass
Here's
for
the-
running from the kernel. Can you
Should I put this back on?
Yes, ideally.
do the microphone? It's okay.
Go ahead, sorry.
Yeah. Can you explain the logic behind where do you choose Cutlass, when do you choose CUDA itself?
Yeah, that's a good question. I mean, I think Cutlass is not like a general purpose like language, right? It's a library for mostly gem kernels. So in VLM we have a lot of different kinds of gem kernels, right? Even attention is kind of just a bunch of fused gem kernels in the end. So I think the simple answer is just if it's a gem, then it's Cutlass. If it's not a gem, it's probably at this point is going to be Triton. In the past, it might have been just CUDA. But they're also, it's not, these aren't like separate technologies. Cutlass is a CUDA library. So you write a CUDA kernel, you use Cutlass primitives. If you need something that's not in Cutlass, you write it yourself. But most of the time it's just going to be a Cutlass thing, or you're not using CUDA anyway, because if it's not a gem, you're using Triton most likely. That'd be like a intuitive, deeper answer. Does that make sense?
All right. Any other questions?
Good work.
Well, thank you. Thank you.